Have you ever wondered why our planet is a sphere? It seems like such a simple, perfect shape for a world to take. The reason is a fundamental force of nature: gravity. When planets form, they begin as massive clouds of swirling dust, gas, and rock. Gravity, the great cosmic organizer, pulls all of this material inward toward a common center of mass. Over millions of years, this balanced pull smooths irregularities, forcing the mass into the most efficient shape possible: a sphere. This is why our Earth, the Moon, other planets, even large stars, all tend to be spherical. Our spherical Earth provides a predictable, stable environment. Gravity pulls us straight down toward the planet's core no matter where we stand. It anchors our oceans, holds our atmosphere like a blanket, and shapes everything from rivers to how our bodies are built. But what if things were different? What if Earth formed not as a sphere, but as a torus, a donut? First, let us get a clear picture of this strange new world. A torus, or donut shape, is fundamentally different from a sphere. Instead of a solid ball, it is a ring of matter rotating around a central void. Imagine a giant, solid bagel floating in space. This world would have two circumferences, a larger one along the outer equator and a smaller one along the inner equator. The surface is a continuous, curved loop, with oceans, continents, perhaps even life. All of this creates a very different kind of planetary geography. From the surface, your horizon would curve up. Stand on the top of the donut, and you could look across the central hole. You could see the other side of the world arching up and over you, a colossal archway across the cosmos. The inner surface would have cliffs and canyons of its own, while the outer surface feels more like a gentle, convex cylinder. The torus splits into distinct regions: the outer rim, vast plains, or even a continuous ocean. Moving inward, the ground slopes toward the inner rim, then drops toward the void before curving back up. Expect canyons, valleys, and steep inclines facing the opposite rim. Where to build? Gentle outer rim or engineered inner cliffs? You cannot just travel straight across. You follow the ring, redefining distance and direction. On our spherical Earth, gravity is simple. It pulls you toward the center. On a donut Earth, that rule is thrown out the window. Gravity depends on mass, and here the mass is in a ring. So gravity pulls toward the densest nearby ring, changing direction and strength as you move. On the outer equator, gravity feels relatively normal, straight down, but a bit weaker. You could jump higher. Buildings could soar. At the top, gravity doesn't pull straight down. You're tugged both outward and inward, leaving a slight, constant tilt underfoot. Dropped objects fall at a gentle angle. The weirdest spot is the inner rim. Gravity is weakest, split between beneath you and the far side of the hole. A gentle push could send you floating. Giant leaps come easy. Paradise for thrill seekers, a nightmare for staying grounded. Physicists model these fields with vector calculus and numerical simulations to predict how motion, rivers, even cities would behave. In short, a planetary funhouse, where down changes with your address. The bizarre gravity of a donut Earth would reshape oceans and air. Stronger gravity along the outer ring pulls most water outward, forming a deep outer equator ocean. Weaker gravity near the hole yields shallow inner lakes and seas. With the moon and sun tugging across the ring, tides become complex, sloshing between inner and outer basins. Some regions see enormous tidal bores, others stay placid and calm. Air, like water, piles where gravity is strongest. Thick pressure on the outer equator, thin along the inner rim. Climb the inner rim and air thins fast. Everest vibes in minutes. The inner hole could trap fog in a calm, misty bowl. Wind is channeled by the donut's shape. Less free-roaming cyclones. More guided corridors. Jet streams might loop the ring, forming near-permanent wind bands. Storms could circle the hole, even become long-lived near-stationary hurricanes. Sunlit versus dark side temperature gaps drive powerful winds, a howling gale through the central hole. Climate scientists would model coupled ocean-atmosphere flows on a torus to predict currents, monsoons, and storm tracks. The path of the sun would create mind-bending day and night on a donut Earth. Assume the planet spins like a wheel on an axle through the center. On the outer equator, a sunrise and a sunset, fairly familiar. At the top, the sun may duck behind the far arch midday, causing a brief eclipse, then reappear toward sunset. Some regions could experience double dawns and double dusks. With an axial tilt, sunlight around the ring varies wildly across seasons. A summer elsewhere could leave the inner rim in a long, cool shadow, a seasonal cold pocket. Inner rim regions may have short days, extended twilight, and a constant reflected glow from the opposite arch. Low-light evolution would thrive. Timekeeping would diverge. Outer rim day-night versus inner rim sun, arch shadow, and reflected glow. Life on a donut Earth must be resilient. Gravity, air pressure, and sunlight variations create a mosaic of environments. Inner rim's low gravity favors towering, spindly growth. Outer rim's higher gravity favors stocky strength. Shadowed regions breed hyper-efficient photosynthesis, even chemosynthesis. Low gravity eases flight. Imagine giant gliders, while land creatures master tilted terrain and angled falls. Humans cluster on top of ring temperate zones. Balanced gravity, mild climate, moderate daylight. Inner rim cities anchor into cliffs, built to withstand strange force vectors. Travel between inner and outer rings demands specialized vehicles or winding passes. Seeing the other side overhead reshapes cosmology, art, and identity, unity or rivalry between inners and outers. A torus planet faces stability challenges. Spin must counter gravity precisely. A fragile equilibrium. Asteroid impacts or shifting interiors can distort the ring, leading to runaway lopsided mass and collapse toward a sphere. The inner rim's weak gravity leaks light gases. Over time, atmosphere thins, unless the torus is massive or dense, a super donut. Powerful simulations, even advanced space games, can model such worlds and their physics. The goal isn't a new home. It's stretching our understanding of gravity, light, and motion through imaginative science. Could a donut Earth exist? Physics says it's highly improbable. Spheres win by nature. But asking what if pushes boundaries. Every breakthrough began by challenging the status quo. We've found worlds with two suns, rogue planets, and super-Earths with exotic chemistries. Imagination fuels reason, mathematics and simulation, are ships for exploring impossible worlds. Scientist, artist, or daydreamer, you belong to the grand human tradition of exploration. So keep asking wild questions. Keep imagining the impossible. You never know where the next what if might lead you.